I should start by saying that I've actually sort of prepared two talks. So I certainly don't have enough time to give both. So what I'm going to do is I'm going to start with the talk I prepared second. And that one's a little shorter, so I may run out of time. So if I do, sorry, I may end early. And if I do, then I'll just start the talk I prepared first. So I'm like I'm doubly organized. That said, if you have any questions, please just ask. And I would much rather answer your questions than get through everything I prepared, which is impossible because I prepared two talks. OK, so let's begin at the beginning. And I should say that all of this is joint work with, or parts of it are joint work, or the parts that I did and the parts that other people did are intermingled in such a way that it's impossible to tell. Joint work with Marc Bell, Vaibhav Gadre, and Rodolfo Gutierrez. But Rodolfo's not here, so it doesn't matter. Ha! That's correct. OK, good. So my goal. Two goals. Goal one, explain the cartoon. So here's the cartoon. We have combinatorics. And we have dynamics. And then we have ways of moving between them. So the way that's maybe easier to understand, and I explained very carefully in my talk that I prepared first, which I'm planning to give second, is that you can go from dynamics to combinatorics using geometry. And the one that I want to talk about first, but I prepared second, is you can go from combinatorics to dynamics using linear algebra. And this is actually... So I've been hearing about this connection going back and forth since I was a graduate student, but I'm not actually a professional symbolic dynamicist. So if I don't understand some of the background or I get things wrong, please just correct me, and I will be very happy. In other words, if you have some dynamical system that you're interested in, you'd like to encode it using symbolic dynamics, but you want to make sure that your symbolic dynamics are good. You want to make sure that everything everything that looks like an encoding really comes from something dynamical, right? So this is sort of a faithful representation of your dynamical system in this symbolic context, right? So that's goal one, and goal two is to be less vague. I probably won't get to this, but the veering automaton, the core automaton is strongly connected. So I believe that you've heard about rosy diagrams already, and you've seen maybe a proof that they're strongly connected in the previous weeks, or some people have, or some people already know that. And so that is supposed to be the thing to think of here. We're giving a different kind of symbolic dynamics for strata of quadratic differentials. So that's the very high level. So now let's go back down and do things from the beginning. So here's part one. So before we do any combinatorics or dynamics or linear algebra or geometry, we must do topology. So fix three things. S equals SG, a surface of genus G. So it was already said yesterday, so I'll just say it again and not write it down. It wants to be connected, no boundary. It wants to be oriented. That's about it. So part two, fix some set of points inside of S, a finite, and this is crucial, non-empty set of points. And now we're going to make contact with quadratic differentials. So fix kappa mapping the set of singularities to, let's see here, z greater than or equal to -1, such that, Gauss-Bonnet holds, if you take the sum of the orders, then that's equal to 4g minus 4, like so. And so then just the easy examples. Maybe I have 4 points of order -1. So this is the stratum -1 to the 4th. Or sorry, this is the topological data that's supposed to represent the stratum of quadratic differentials. And maybe 2 more examples just to keep things interesting. How about, let's have 4 points here, +1, -1, +1, -1, like that. And so this is the stratum -1 squared +1 squared. So I just, instead of writing down -1, -1, -1, -1, I just write the exponent here to represent how many times it appears. And maybe one more example, which is terrifyingly large. How about -1, 0, 5? Like so. So there's some examples of topology. So let's now do some of the combinatorics. So part 2, combinatorics. 1, veering triangulations. So this is the main subject of the talk. This is what we want to be studying. So here it is. Suppose, yes, sorry.
What's the index of this?
It's greater than or equal to -1. So if it was non-negative, I would have written n, but I could have written greater than or equal to 0. Right, sorry about that. So we don't allow poles of order higher than 1. That's the way to think of this. Pole, at worst, simple poles. And we do allow zeros. Sorry, we do allow singularities where the order is 0, so they're not zeros. They're just marked points. And I actually had some of those. I had one of those in my example. Okay? So this doesn't represent a 0 of the quadratic differential or a pole of the quadratic differential. It's just like, I'm interested in that point, so I'm going to put a dot there. And I can have as many of those as I want. Why don't I do one more example? Here is the torus, and I have a bunch of marked points, but they're all just ordinary marked points. They're not zeros or poles. Does that answer your question? Great. OK, so suppose, not suppose, fix a collection of 4g minus 4 plus z arcs cutting S into a collection of triangles, all vertices at ZS and all Z in ZS vertices. Okay, so usually when you think about a quadratic differential, maybe it has some decomposition into polytopes, and the marked points could be in the center of the, in the center of the polygons. We're not going to allow that. All of the singularities have to be at vertices. All the vertices have to be at singularities. Right? We control the combinatorics. Here we go. 1, 2. This was probably a terrible idea because I didn't have it in my notes. So far, so good. That's just 3 edges. That's not enough, right? I need one more. And this is not in my notes, so I'm not quite sure where it goes. But I think it might go here. Like that. Okay? So that's 4 edges. And what does it do? It cuts it into I'm worried that that's wrong because there's a 2 here. So I'm not done. And I apologize for that. And I'm not going to fix it. But in my notes, I didn't have this example. In my notes, I had this example, which is easier. I got too ambitious. So how many am I missing? I'm missing 2 more edges. A, B, A, B, A, B.
You can claim that this is a homework
Exercise. That's why you're in charge and I'm not. Very good. Okay, exercise. Excellent. Veering triangulations. Next, we color every edge red or blue. So let me just give you a mnemonic. There's the color, red or blue. Ha, here's red and blue. And what do they mean? They represent the slope. So everything is combinatorial. So we don't actually have slopes in the sense of Euclidean geometry, but that's what they represent. Positive or negative. Or they represent the veeringness, which I hope to explain by the end. And this would be right veering, and this will be left veering. And so what are the, and there's a rule, no monochromatic triangles. So there are only 2 triangles that are possible, given the rule. So here is one of them. And here is the other one. Okay? So this is a majority red triangle. That's a majority blue triangle. And those are the only 2 kinds of triangles. And then I need one more thing, which I think I'll draw all the way over here. So a forward flip. Oh, so this is combinatorics. What am I at? 1, 2, 3. Flips. Suppose E is an edge of either color, and A, B, C, D are the neighboring edges. So what I'm going to do is I'm going to choose one end of E, and then I'm going to walk anti-clockwise around E, labeling the edges A, B, C, D as I go, right? Colored, blue, red, blue, red. So because this string, if you shift it by 2, you get the same string. It doesn't matter which end of E I start at. So here's the only thing that you can get, which is I start with E, like here. This is E. And it's either color. It's red or blue, but I don't know which. And then I'm supposed to see something which is blue, then red, then blue, then red. Like so. If I see this, then I can do a forward flip. And so the forward flip changes nothing about the neighborhood, but it changes E to E prime. So let's see here. I change nothing about the neighborhood, so I still see blue alternating with red. And I don't learn the color of E prime. It can be either color. Okay? This is the only move allowed in veering triangulations. You can just do forward flips. And of course, well, you could go backwards, but that's called a backwards flip. And that goes against the arrows. Yeah? So then may flip E to E prime, either color, as shown in the figure. So define. So this is not the right object. Yes, question?
When you say either color, are you still keeping the color the same, or
No, there's 4 possibilities, right? So this starts red or blue, and it ends red or blue or blue. It's not correlated at all. Okay? Either color independent of E. All right? Define AV kappa. Oh, sorry. I left off kappa. I'm going to put it right here. There's 2 rules. No monochromatic triangles, and one other rule which I forgot, and I apologize. Stop it. There we are. Rule about Z in ZS, there are, let's see here, 2 kappa Z plus 2 alternations between colors. So let me just draw an example of that. So here is some red edges, and here are some blue edges. So there's tons of edges. I don't care how many edges, really. But what I do care about is that when you go from blue to red, or from red to blue, in this particular diagram, you only do it twice. And that's because here, kappa equals 0, right? 0 plus 2 times 2 is 4. You see 4 alternations between red and blue. And then I'll do one more example, which is kappa equals -1. And I think I chose to do red like this and blue like this. OK, there we go. Right, only 2 alternations, and that's because it's a pole. Yes? Each edge, so no, they represent saddle connections in the quadratic differential. Yeah? And yeah, that's the, and each bunch of edges of a single color, that's like 1/4 plane. Although not quite, because no, red is supposed to be positive slope, so it can't be perfectly vertical. And blue is supposed to be negative slope, so it can't be perfectly vertical either. So there's always a gap, which has appeared in the literature already, between positive slope and negative slope. A famous gap. Aha, and there's big colors now. Excellent. OK, so I recover kappa. So if the triangulation has those properties, then we say that it belongs to the stratum for kappa. Yeah, define the graph automaton with vertices being veering triangulations of S Z kappa. Right? So to be a veering triangulation, you have to be a triangulation, you have to have colors, no monochromatic triangles, and you have to obey kappa. Right? You have to have the right number of alterations at every singularity. So let's just orient E. That's making a choice, but as we'll see, that choice doesn't matter. So what I do is I go to the head of E, and I look on the left-hand side. And that says, oh, I'm going to call this A, B, C, D. That's the way I'm going to name them. And the requirement is that it's blue, red, blue, red. Yeah. Now, if you orient it the opposite direction, it turns out it doesn't make a difference. And so you're good? OK. Yeah. please do ask questions. I don't promise to be able to answer them. Right. Big veering triangulations and edges are forward flips. So maybe I won't make fun of this. I just defined it, so it's too early to make fun of it. But it's too big, and it's got a lot of junk in it. So we don't like that. So we want a way of kind of getting rid of the bad veering triangulations and keeping the good ones. So here is part 4, linear algebra. So we have edge variables. So I'll draw both of them just for fun, but it doesn't make a difference. So here are my two types of edges. And maybe this is E and this is E prime. So I have two variables, xe, ye, and xe prime, ye prime. Two real variables per edge. All right, so this is trying to, I forget who asked the question, somewhere over there. They're not representing something complex. They're representing saddle connections. They're representing something in the Euclidean plane. Yep. And then positivity. E, ye greater than 0 for all E. And finally, kind of what's going on, the triangle equalities. Oh, I'm supposed to say something about positivity. No negative numbers are allowed. So you might wonder, like, how am I going to represent, like, when the edge goes backwards, right? Like if I'm going, they can't both be positive, right? So the color tells you how to flip the signs in order to actually make it fit into the plane. They could both be positive, or they could both be negative. Here, there's exactly one positive and exactly one negative. The color tells you the signs. And actually, it doesn't tell you the signs. It tells you the signs up to 180-degree rotation, right? Which makes sense because we're talking about quadratic differentials at the end of the day. Yes?
What edge is this? Is this an edge in the graph? Or
This is an edge in the veering fix S, Z, kappa, T. So I'm talking about this triangulation, the triangulation T of the surface S. Great, edge equalities. So now I have so here are my triangles, A, B, C, A, B, C. And it's just combinatorial, right? You can rotate them in the plane however you like. You could make them wiggly. That doesn't matter. This is the rule for producing the equations. XA is equal to XB plus XC. So you could think, if I have green, that maybe there's some vertical foliation, which is telling you that the width of A is the sum of the widths of B and C. And similarly, if I had purple, but I didn't request purple ahead of time, then maybe there's some horizontal foliation, which is telling you that the height of C is equal to the height of B plus the height of A. And this looks very similar, right? A is the widest one. XA equals XB plus XC. But this time, it's B that's the tallest one. YB equals YC plus YA. Note that the set of solutions is a product of cones. Okay, so the x's and the y's, they don't talk to each other at all, right? So we have everything's in R to some high power. Yeah. Everything's positive, so it's living in the positive orthant. And everything's linear, right? So that's telling us that we got a bunch of cones, right? The solution set's a cone, but it's a cone that breaks up as a product. Let's call it VT cross HT, right? The vertical cross horizontal cones. So definition, T is core if the dimension over R of Vt equals the dimension over R of Ht equals the dimension over C of Q kappa. Okay? I'm ignoring some issues about whether things are orientable or not, whether things are hyperelliptic, what the spin is. Let's just not pay any attention to any of those issues. This is the basic definition of what it means to be a core triangulation. So, these are conditions. It's actual, it's Cartesian product, yeah. Right? You can sort the variables into the, oh, direct sum. Well, this is a Cartesian product, but you want me to do this. It's the sum. Oh, come on. It's finite dimensional. Stop that. No. Or I hope not. Excuse me. Right. So this is a purely combinatorial triangulation. And then I'm going to say, OK, let's just invent some variables, the edge variables. And let's, for no particular reason, require them to all to be positive. And every time I see a triangle, right, I'm going to have these requirements. So this positive number has to be the sum of these two positive numbers. And this positive number is the sum of these two positive numbers. So I'm not, right, this is the big one. So it's the sum of these two. There's no negative numbers in the picture. Yeah, thank you. Lengths are positive numbers. Is there another question? Okay. I've been very careful to not talk about this at all. I sort of assumed that it had been discussed in a previous life. So here, Q kappa is the stratum of quadratic differentials with, I don't know, numerical datum kappa. So if I have time to give my second talk, then I will give a kind of more hands-on definition.
Is it something like you want to see if you can find such a triangulation for this diametric induced vector?
Yes. So every triangulation which satisfies all these things and maybe and lives in the interior of this polytope, that actually will give you a quadratic differential. Okay. Yes. Sorry.
First one is if I give you a veering triangulation, can you tell me if it's core without computing these polytopes? It's not an operation.
This is linear. To compute the dimension of polytopes is linear programming.
Sure.
So it can be done.
But okay, there's no single common.
I do not know any shortcuts. I just ask that I do linear programming over and over again.
Second question is if all kappa are multiple of 2 pi, you have a mix of abelian differentials and quadratic differentials.
So just because everything is even doesn't mean that you're. I said, I was standing here and I said, I'm not going to talk about orientability.
But in your set of triangulation, you have some that.
Yes. So you need to. I was being correctly vague, right? if you put some decorations here, you get the right stratum. And there's ways to detect the extra properties like hyperbolicity or spin or orientability just from the triangulation, from the combinatorics. Those are purely combinatorial things.
Yeah, I was worried, but you can have something not in the core of an abelian differential that would satisfy this equality.
Why don't we discuss this afterwards?
When you, so who is bigger, which edge is bigger is not part of the combinatorial data.
The thing that's part of the combinatorial data is the colors. But let me answer your question in a better way, which is, in any triangle, there's only one alternation. Oh, by the way, the surface is oriented. Not just orientable, but oriented. So I know what it means to walk counterclockwise around a triangle. In any triangle, there's only one alternation between red and blue. So that's where there's a horizontal separatrix, which should be purple. I'll draw it in white. What's that? Orange. Brilliant, thank you. Actually, it should be purple because purple is the opposite of green on the color wheel. But anyway, orange, right? And there's only one alternation between blue and red. So that will be the green separatrix. Here's the alternation between blue and red. That's the green separatrix. Here's the alternation between red and blue. That is the orange separatrix. So the combinatorics tells you how the triangle wants to be situated in the plane. It doesn't say that you can lay out the triangle, right? Maybe if I choose the edge things poorly, blah, blah, blah. If you satisfy these equations, then you can lay the triangle out in the plane. And hence, there is a quadratic differential. Does that answer your question? Great. Here, this is the definition of core. Theorem. Or definition. Sorry, definition. A, C, kappa is the automaton of core triangulations. So this is a subautomaton of the veering automaton. And this is, of course, much smaller. A lot of the time, you don't get the right dimensions. Most of the time. Theorem. The components of A, C, kappa are, so first of all, they're strongly connected. So what does that mean? From any vertex, you can flow forward to any other vertex.
What is the component?
It's a connected component. It's a graph, so it has connected components. Are strongly connected, and in 1-to-1 correspondence with the components of Q kappa. And maybe now you also know how to prove the theorem in addition to the statement. Here's the red thing. So I think I'm just going to leave that stuff up because I don't want to bring this board down and cover everything. So that ends the discussion of the combinatorics, I think. I should probably check my notes. I am supposed to do an example. So I will not depart from my notes. I will do the easiest possible example. I'm going to erase just a tiny bit more.
While you're erasing, can you give an idea of the size of this graph?
If there's time, I will show some pictures at the end. But yeah, I don't know how quickly it grows. It grows really fast, right? So it's got some, yeah, I don't know, is the short answer. So example, and I'll cheat. I'll look at kappa equals 0. So this is actually maybe an easy exercise. So I have to give you two triangulations of the torus. So here they are. And then I have to tell you how to do forward flips. So there's a forward flip here where you turn one red edge blue. So I'll call that a red-blue flip. I turn one red edge blue. Here I have a flip where I turn one blue edge red. There's going to be a forward flip here where I take a blue edge and I flip it forward to another blue edge. And there's one edge here, one forward flip here where I take a red edge and I keep it red. And you can kind of see at least this arrow right here, right? I take this edge and I'm doing the Teichmüller flow, and eventually this thing becomes too long and it wants to flip forward to this vertical edge, which is still red. Yeah?
How do you flip it so that you change all the five edges? You can only change one edge.
I only change one edge at a time. That's right. And
you do that flip and that flip, you are changing all the five edges.
eventually all five edges will change, because who's in the center, who's forward flippable, changes. If you do a forward flip on an edge, it is no longer forward flippable, and you must flip some other edge. Right. After a forward flip, yeah. And now I think I've stalled long enough, so the board is dry again. Good. So now I am supposed to go on to there's only two triangulations in this automaton. So if I flip this edge, I can then color it red or blue. If I color it red, then I have a triangulation that's isomorphic to this one, combinatorially the same. And if I make it blue, I have a triangulation which is isomorphic to this one. Yeah?
But presumably you can have more possibilities for who is larger, who is smaller, and so on. So
yeah, so the out degree is not necessarily just 2. That's right. So and maybe I should just show the, OK, I want to say just a word about the geometry. And I forget what thing I'm on, so I'll just pretend that I'm on X geometry. Suppose X, ZX, Q is a, actually I'll erase the Q, who cares about the Q, is a quadratic differential, is a flat surface. Define xt, z xt in the usual way. Xt equals gt of x equals e to the t. This was already defined in Anya's talk, but I'm doing it again, like so. So x equals x0. OK, so this is a Teichmüller ray. For any xt, we form the Voronoi cells. So what are these? We take vz equals x in xt such that the distance between z and x is equal to the minimum of the distance between x and w in z. So let me just do my big example. And I should say which distance. This is the L infinity distance. So here's my big example of computing Voronoi domains. And these things, the bisector is what you get. So first of all, the center of the square is equidistant from all points on the boundary of the square, because the square is the unit circle in L infinity. In L infinity. So now I'm just going to kind of draw what happens. So there, a nice perpendicular bisector. That's not unexpected. So that's the last nice one. The perpendicular bisector between these 2 points inside the square looks like this. In other words, in L infinity, perpendicular bisectors aren't straight lines. They are crooked lines. They have at most 3 parts. The perpendicular bisector between these 2 points is something like this. And between these two, right here, it's something like, and then down. OK? So that is a picture of the Voronoi decomposition. This is, if this is A, B, C, D, oh, I use those for edges, X, Y, Z, W, then this is a bit of VW, Vx, Vy, and Vz. So I would like to have 2 conditions. Whatever. Let's not say the conditions. Let's just say what happens. This is just a local picture. It's a tiny little square inside of my... It's not a torus, no. So define given x zx quadratic differential, there is, if it's nice enough, which is nice, has the various properties, there is a canonical Delaunay for L infinity triangulation of x zx. So this is the arrow which takes me from dynamics, from geometry, to the combinatorics. So this one's actually not very nice. And the reason why is because this W is on the same boundary of the same square as these other 3. So maybe I should just say what nice is and quit and show the pictures. Nice. X zx is keen. No 2 singularities on any vertical or horizontal ray. Right? I'm in the geometric situation, so I know what vertical and horizontal means, and I know what the positions of the singularities are, so I rule out this bad behavior. That prevents x from being directly above z. And why is that bad? Because the bisector is not one-dimensional. X, Z, X is Delaunay. What does that mean? No 4 singularities on the boundary of any square. Again, it's a quadratic differential, so I have the geometry, so I know what it means for a region in the quadratic differential to be a square, right? So most squares, they're very small, and they have no singularities on their boundary at all. So you blow the square up, right? And if it meets, it can't meet 5, because if it met 5, there'd be 2 singularities on a single vertical or a single horizontal.
What's wrong with having 4 singularities on one square?
The dual isn't a triangulation. The dual has a square in it, has a rectangle in it. And I don't like rectangles. I want everything to be triangles. OK, so if I have these 2 properties, then I can apply the flow, right? And at all times, I'll have these 2 properties, except at certain times, a discrete set of times, and at those times, I don't have the Delaunay condition. So instead, I'm doing a forward flip. Because, OK, so I anticipated this question. So thank you for asking it. So I think I'll stop here, because I'm out of time. But if there are any questions, I'd be happy. No, I've started the second talk. The second talk was about the geometry.
Then you can make a third talk.
A third talk. So why do I like L infinity is the question currently. So metric, ball, remark. So there's L1, and that's the ball, right? And you understand that I don't like this. This is very unpleasant. Then there's L2, which I hear you saying, like, this is very nice. There are actual papers which are written about L2. Yes, Delaunay triangulations in L2. This is round. Invariant, it's too round under rotation. That's bad, right? The Teichmüller flow knows the difference between vertical and horizontal. You're not allowed to rotate one to the other. Right? I mean, you are, but if you do, you're switching time going forwards and backwards. And dynamical systems, that you're not just allowed to do that. But L infinity, our friend, the biggest one of all, knows vertical from horizontal. So the flow doesn't preserve the roundness of the square, right? It turns it into a rectangle. But that's a good thing, not a bad thing, right? That tells us that where the flips are going to happen. I had another remark. Oh, yes. So actually, the L infinity Delaunay triangulations are studied in the computer science literature. And there's a nice paper, which is, I think it's called the last Delaunay triangulation. Because there's this one, da, 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 da. This is the last one. So they talk about finding Delaunay triangulations of point set, in L infinity of point sets in the plane. So if you want to turn quadratic differentials into Delaunay triangulations, you have to do something more sophisticated because you have topology. But you can follow some of the ideas. Yes? Sorry.
Maybe one more argument for L infinity.
Yes.
If you look at the Delaunay cells in the modular space,
Mm-hmm.
L infinity, the walls are linear in the coordinates of the triangle, which is not true for L2. You got quadratic equations. So it's much nicer.
What's that? So in SL2R, we're interested in studying the dynamics of the SL2R action on quadratic differentials, right? So this one is very nice with respect to rotations. This one is pretty nice with respect to the hyperbolic transformations, which are actually, that's a non-compact action as opposed to the rotation, which is a compact action. No one's very nice with respect to shearing. So I think there's papers about that. This is not nice with respect to, this doesn't respect any kind of SL2R anything, as far as I can tell. I should stop there. No. I have to continue. I promised some slides, so maybe I have another 12. Why do I have another 12 minutes? I thought I had 50 minutes, and it's. Okay. Well, how much time do I have left? Yes.
So can you explain, since you've got 12 minutes, the connection a bit more precisely between the geometry and the quadratic differentials and the combinatorial feature?
Since I have all this time, maybe I will give a definition of quadratic differentials and say a little more slowly how to go from quadratic differentials to the coding. Man, I thought I was out of time, and I rushed. I apologize. OK, since I have all this time. Did that, sort of. Did that. Did the big example. Did that. OK, so let's just recall. I'm completely confused now. But Anton, you'll you'll stop me before it's time for slides, right?
No, you 10 minutes, and within this 10 minutes, you have to do everything, including slides. Go on.
So you know about overage?
Yeah, overage.
Regulation time, all the time that you wasted gets added on to.
Since there have been a lot of questions, let me just say a word about what a quadratic differential is. Fix a collection of polygons P with marked points in the plane. Let's say marked points Z P. So here's my collection. We assume we have edge pairings of the form, let's say phi EF sends Z to plus or minus Z plus C. Okay, so for any two edges with correct orientation convention, let's not worry about that. I want to glue them together by some half turn, a half turn, or translation. And the one requirement is that the markings must be respected. So I'll just draw a simple example, if I can erase these colors. Very confused. Okay, so example. Here's a single polygon. And I want to identify opposite edges, but let's have a few bits of color first. Here we go. Let's put a marked point here, because why not? Nothing stops us. Let's put a marked point here. And let's put a marked point here. Just there, like that. Why not? So glue opposite edges and note that marked points are preserved. So remark, quadratic differentials, these flat surfaces, half-turn surfaces, are only defined up to scissors congruence. G. So then a special thing to do would be to have all the polygons be triangles, and then you get a straight triangulation of a quadratic differential. If all P ZP are triangles, we get a straight triangulation. So now I can redo what I did before, and I can explain why these are the right conditions. I take the Voronoi decomposition of a quadratic differential. So lemma, if x Cx is keen and Delaunay, then VZ is a cell. Okay, I just need Keen for the Voronoi decomposition to be a cell decomposition. And the dual to VZ. And what is the dual? When two Voronoi domains share some edges, and they don't share any two-dimensional stuff because I'm Keen, then I connect them by straight lines. Right? So here is positive slope, here is positive slope, here is negative slope, here is negative slope. And this is a geometric picture. Those are actual straight saddle connections. And we notice that this is not a triangle. Right? This is a square. That's bad. The dual to the is a straight triangulation. This business of having 4 singularities on the boundary of a square, that's exactly what's ruled out by Delaunay. Color these. So that's the lemma, color by slope. OK, so this is the recipe for how you go from the geometry to the combinatorics. And we've already discussed how we can go from the combinatorics to the geometry using linear algebra. So now I should just show the pictures.
Also, using the time on the screen is doing that.
Yes.
You have constructed one more combinatorial machine.
Yes.
So there was rosy graph, whatever. Can you explain what is the rule in the sense? What your machine serves?
So there are 2 answers to that question. So the first answer is a quote from John Smiley. So John said, let 1,000 induction algorithms bloom. Right? So it's always good to have another way to do induction. You don't buy it? No, you don't agree, right? So an IET is combinatorics in a cover of the stratum, because you have to pick a singularity and a horizontal separatrix, right? This lives downstairs, or in the original stratum. So that's the one motivation. Does that answer your question? OK, great. And now I'm supposed to just go over here, and let's do them in order. So we've already seen this one during the talk. The green dots are the triangulations, and thank you very much. And there's just 2 of them. And the edges are decorated in the way I described, right? So this is a completely red edge. So that means that the flipping edge started red and stayed red. And going between them, you have these edges which flip from being blue to being red as you go across. The 2 here indicates the number of automorphisms. And let me go to the next one, which is also quite pleasant. Can I just zoom in? Double click. And full screen. I'm going to regret this, aren't I? Because it's all in French. Control L. Yeah. And then I'm going to have to get out of this somehow, but that's fine. So what's the difference in colors here? Everything here is a core triangulation. But there's an additional property that I mentioned geometrically, but I didn't define combinatorially. And the additional property is being a Delaunay triangulation for some quadratic differential. So these orange dots, they are core, but they are not geometric triangulations for any quadratic differential at all. So they're in the core automaton, but they don't belong in the geometric automaton, which I didn't define. All right? And you can see that they really don't belong, right? In some sense, if you start at this Delaunay triangulation, there are 2 edges you can flip, both blue, and they take you into this unpleasant world where you're core but not geometric. But notice there's only one thing you can then do, which is to flip the other edge, and now you're back into the geometric world. Yep. So if you were willing to do multiple flips, which are much more complicated to code up, so we're not willing, then you could just restrict yourself to the geometric automaton, just to the green vertices, which are honestly Delaunay triangulations for some quadratic differential. Yes?
What do the flips correspond in terms of the quadratic differential?
OK, so that's an excellent question. Flips don't change the quadratic differential at all. They are different triangulations on the same quadratic differential, right? So if you have a set of edges, right, and you do a flip and you rewrite the height and the width of that new edge in terms of the old ones, then you're representing the same quadratic differential. Every quadratic differential has infinitely many different triangulations on it. It's only got one geometric triangulation. So if you do these two flips, you'll find a non-geometric triangulation of that quadratic differential. But you could do the Teichmüller flow and make it geometric. So there's two ways to think about it. We fix the quadratic differential and we do flips, and we see where we get. And we can get to lots of triangulations this way. Oh, and by the way, those live upstairs. This is downstairs in moduli space, right? If you actually just fix a quadratic differential and start doing flips, you'll get infinitely many really different triangulations. They may be homeomorphic to each other in pairs, but then you're trying to work downstairs. The other thing you could do is you could say, here I have a quadratic differential, and it's got a nice Delaunay triangulation. I could start flowing it, right? I could stretch the horizontal and squeeze the vertical. And then it's like, oh, it's time to do a flip. And actually here you do a double flip, and you get to a new Delaunay triangulation. Now it's time to do another flip. It's time to do another flip. It's time to do another flip.
Would it happen infinitely a number of times?
So if you start being keen and Delaunay, then you will flip infinitely often. Yeah, you will never stop.
What is the stratum?
The stratum of this picture is, well, it's 0, 0, because I've memorized it. But if I get out, then let's go back to the, thank you very much. So you can see the strata which are listed along the side here. So let's just look at one more example. I think it's this one. Yeah, there. OK, so this is 2. And I think we could, if we open it, it refuses to display on the screen, actually. So maybe I should have said that first. That's not very nice. So maybe it's better to look at it in the, oh, there it is.
Oh, it was.
There it was. Let's kill it. Yes, really kill it. There, so we can actually see the system previewer is better than the actual previewer. So you can see lots of interesting structures, right? If you could zoom in on this, which you can, even if this is preview, you can see there's little green dots. There's some orange dots, right? There's many more orange dots than green dots. So geometric is yet another slice down. It's still going to be growing exponentially, but it's yet another way to cut down on the size. And you can see that there's these edges. You can see there's lots of kind of cube structure. And you can also see that there's these, oh, by the way, I wanted to say this. You see these two kind of little antennae? That is not an accident. There is a z mod 2z involution on the automaton, which is rotation by 90 degrees. Yeah. So, but then I just wanted to say I have no idea what these big structures are. There's these giant loops. There's easy ways to cut. There's all kinds of stuff going on. So thank you very much for your attention.